When we're talking about how our senses work, the biggest myth, in my opinion, is that they reflect the world as it actually is. Today, we're going to tackle that myth. And what we're going to find is that, yes, our tinkering Mother Nature did leave us with a powerful sensory system. But it's not a system that captures the world as it is. Instead, it's a system that samples only a tiny portion of the environment, takes many shortcuts, and fills in details to give us the illusion that we perceive reality objectively. For the sake of clarity, I'm mostly going to focus on the sense of vision today, the evidence of our own two eyes. So let's get started. Of all your senses, vision takes up the most cortical real estate. If you can see, that is. You've probably encountered the idea that people who have lost a sense, or never had it to begin with, can adapt other senses to give them the information they need to navigate the environment. And it's true that there are stories of remarkable individuals who have other heightened senses in the absence of, say, hearing or vision. One of my favorites is the story of Ben Underwood, who lost his sight thanks to cancer in both eyes at the age of 3. But he became a real-life Batman. He learned to use echolocation to see the world around him. When he walked or even rollerbladed down the street, he made a clicking sound. And by listening to how that sound bounced off of objects, he could tell where the sidewalk ended, where there was a parked car, and even where the garbage bins were. Sadly, the same cancer that took his vision took his life at age 16, but not before he had made a deep impression on scientists and laypeople alike. A 2010 study of how blind people perceive speech also provides support for this idea that stripping away vision can leave a person with better hearing, partially explaining the talents of blind musicians like Stevie Wonder and Ray Charles. I've often been accused of speaking too quickly, and it's a habit I fall into when I get overly excited. But even I can only say up to 6 syllables per second. When you hear the caveats at the end of a radio commercial for a lending company or a new drug, that sped-up speech is about 10 syllables per second. But blind people can understand speech up to 25 syllables per second, which is faster than humans can talk. And to most of us, it just sounds like noise. These stories illustrate something fundamental about how our brain perceives the world. It's much more complicated than taking a picture or recording a sound. And the idea that we see the world as it is, or that we hear sounds just as the sound waves behave, is a myth. Let me show you what I mean. How big do you think your field of view is? That is, how well can you see? Assuming you have perfect vision, or vision that's corrected for its imperfections by glasses or contacts, how much of the room or space you're in can you actually see clearly? I feel as though I can see about half of the room, everything that is in front of me, and a bunch of stuff on each side. I don't have eyes in the back of my head, but don't tell my kid. So I can't see behind me, but I'm pretty confident that if a gorilla popped into view in the half of the room that I'm facing, I would see it. But I'm a trained psychologist, so I know better. Imagine for a minute what it would actually take to be able to see with enough detail to distinguish, say, words printed on a newspaper page, everything within view. We would have to have an incredibly precise way of translating light into a neural signal with spectacular resolution. Then we'd have to have an enormous part of our brains devoted to processing all those data points. And then we'd have to have the ability to focus on many different things at once, as all of these data tax our attentional resources. Instead, our retina, where light from objects is translated into neural signals, is a flat sheet. It's two-dimensional. So we already have a problem. We need to infer depth from other cues, like which objects occlude each other, how big they are relative to one another, and where they are in one eye versus the other. What's more, the optic nerve that takes the information from the retina and sends it along to the rest of the brain has about 1 million fibers. Each fiber represents information from one part of the visual field. You can think of it as a pixel. So your eye has a resolution of about 1 megapixel. That's a pretty inadequate camera by today's standards. My phone's camera is 8 megapixels, having access to 8 times as much information as my eye. The way that the eye gets around this relatively poor resolution is by concentrating much of its fibers in the center of your field of view, so that the resolution where you focus your eyes is much better than everywhere else. And yet it feels as though the entire visual scene in front of my eyes is projected onto my brain with the same resolution. I don't see the fact that only a small portion of the visual field is being perceived with enough detail to allow me to read. But if I just stare at one point in space for a second and put a book or an iPad or any other reading material just slightly off to one side or another, I quickly realize that I can't see much at all. It's too blurry to read. I have to point this out to my undergraduates. It's not something they come to class already knowing. The first time I realized that this was the case, I have to admit I was pretty amazed. I just don't see the world as this tiny piece that is detailed, surrounded by all this blurry stuff. I see it as having a uniform resolution. And that's because my brain is fooling me. Not intentionally, of course. It is simply adapted to give me the information I need to find food and mates and evade predators. The brain perceives only a small portion of the available information from the world and fills in the rest, giving us the sense that we can see, hear, smell, taste, and feel much more than we can. This principle, the tunnel vision coupled with the filling in, is a common theme in perception. Even though our skin takes up more surface area than any other organ, it's our eyes that we seem to rely on most when it comes to experiencing the world around us. And yet, compared with eagles, who can see 4 to 5 times further than we can, or chameleons, who can swivel their eyes to see 360 degrees, or the colossal squid that comes equipped with a built-in flashlight above each eye, we seem to be just stumbling around in the dark. Even so, our visual system is truly amazing. Consider, for example, the fact that we can recognize common objects from any angle and track a tiny white plane across a pale blue sky, and perceive a handful of M&Ms as maintaining their colors as we switch the lighting that illuminates them. In fact, performing these feats is so complex that no artificial intelligence machine has yet been built whose vision is as good as ours. In order to accomplish these impressive visual feats, a huge part of our cortex is devoted to the processing of visual information, more than any other sense. How the visual system develops also tells us a bit about how the brain works, because it's a system that, like much of the rest of the brain, has predispositions at birth, but without the right experiences, fails to develop normally. That's why if an infant is showing signs of impaired vision, say his eyes are crossing because the muscles that move the eye aren't developing properly, it's important to diagnose and treat the condition as early as possible. A child whose eyes don't learn to work together in the first 3 years of life, for example, might always have vision problems, particularly the ability to use both eyes to judge the relative depth of different objects. You might remember that the birth of neurons is just the first step in building a brain. The next step is to guide those neurons to where they need to be in order to make useful connections. And the third step is to wire up those connections so that they make up a functioning network. It's this last stage that is most dependent upon experience. As I've mentioned in another lecture, neurons that are isolated, that aren't receiving any messages from other cells, die. So in the case of the child whose eye muscles aren't working together properly, the cells that use this information to infer depth won't be getting the right signals. Those cells then are either going to be assigned a different task or they're going to die, leaving the child unable to perceive depth using stereoscopic cues. This same idea applies to many aspects of brain development, but vision is particularly sensitive to what we call a critical period, a window of time during which the right inputs need to be provided, or else the system will never develop properly. That's why restoring sight in adulthood is not as simple as removing scales from the eyes, as the New Testament suggests. The visual system is a great tool to illustrate other principles of perception too, particularly the shortcuts and filling in that we're largely unaware of. So I want to take a bit of time to explain how it works, and then we can discuss the implications. Visible light travels in the form of photons, little tiny packets of energy that bounce off of objects that they encounter. Now, I say visible light because waves of light can be very short or very long and every distance in between. And we humans can only perceive a small portion of this continuum. We've adapted to perceive photons of light that tell us what we need to know to find each other, recognize social signals, avoid predators, and other ways that nature can harm us, and so on. A tiny portion of the photons that are bouncing off of the external world make their way into our eyes. They're focused by a lens onto the back of our eyeballs, where cells called photoreceptors ultimately trigger a cascade of neural signals. We have two types of photoreceptors, called rods and cones, because of how they're shaped. They're also distributed differently along the back of the retina. Where you focus your eyes, that part of the retina is largely populated by cone-shaped photoreceptors that ultimately provide enough information to distinguish colors. The cones in this part of the retina are stacked very close together, and they're connected to upstream cells in a 1-to-1 ratio. That is, for every cone, there's one upstream cell that captures its signal and passes it along. Outside of this region, cones are more sparse, and the rod-shaped photoreceptors are more common. Rods don't have the same luxury of a 1-to-1 relationship with their upstream cells. They have to share their signals with other rods, such that a handful or more rods send signals to the same upstream cell. And rods can't provide information about color. What they see, if you will, is black and white. This pattern of retinal distribution and convergence on upstream cells gives rods and cones different roles in visual processing. Cones are responsible for our high acuity vision, the small part of the visual field that we're able to see with enough resolution to read words, and so on. By maintaining a 1-to-1 relationship with upstream cells, they can send specific information about light in a small part of space. And there are 3 types of cones, each more sensitive to a particular part of the wavelength spectrum. By comparing this relative activity of these different types of cones, the visual system can distinguish colors. Rods, on the other hand, give us better sensitivity to light. Since a handful or more rods converge onto one upstream cell, if any one of them detects a photon, as would be the case when the light is faint, say from a distant star, that upstream cell receives a message. But the cell doesn't know exactly which of the rods sent it, which is why your vision is blurrier in the periphery. And there's just one type of rod, so no color information. These upstream cells in the retina are arranged such that if a photoreceptor in their receptive fields detects light, they pass along the message even further upstream. This information continues to the thalamus, in the middle of the brain, and then to the back of the brain, where the occipital cortex is arranged in modular columns of cells. These columns have cells with very specific tasks. Along one set of columns, you have cells that respond best to bars of light in specific orientations. Along another, you have clumps of cells that process color information. Another region detects motion. And then further upstream, you have brain regions dedicated to recognizing objects. We now know that these regions are highly specialized on the basis of 2 converging lines of research. When we stimulate them in animals or in patients with epilepsy or other issues that require the implantation of electrodes, we see specific reactions. And when these regions are damaged with circumscribed lesions, say from a tumor or a bullet, patients have specific impairments, which argues against the myth that we see the world as it is. If that were the case, then we wouldn't see such specific impairments. You'd either see that part of the visual field or you wouldn't. For example, some patients have such specific visual impairments that one can't help but marvel at how modular our visual system is. One example is prosopagnosia, or face blindness. The ability to recognize faces is a skill that some people are much better at than others. I'm sure you know someone who seems to be able to recognize fairly obscure actors and tell you immediately what TV shows or movies they've done. Or maybe you have a classmate who can instantly recognize her peers at a reunion, even if she hasn't seen them in decades. That person, by the way, is definitely not me. At the other end of the continuum, some patients with severe face blindness can't even recognize their family members from their faces alone. These patients learn to use other cues to distinguish people, like their voice or gait. The great late neurologist and my mentor and friend, Dr. Oliver Sacks, was one such person. I remember going to his 80th birthday party, where he individually greeted each one of his many guests. There were more Nobel Prize winners in that room, I think, than in any other enclosed space at one time. But only after his assistant whispered their names into his ear. You might not find that all that remarkable. Many of us are bad at recognizing acquaintances, especially outside of the context in which we generally interact with them. But Oliver needed help on every name, even his closest friends and family. But hand him an obscure fern and he would recognize it immediately. His problem wasn't that he didn't see faces, it's that he didn't recognize them. There are also patients who lose the ability to detect motion. Oliver himself found a beautiful description of one such patient, which he quotes in a footnote in his book, An Anthropologist on Mars. The original case study was published by Josef Ziel and his colleagues in 1983. Here's the description. She had difficulty, for example, in pouring tea or coffee into a cup because the fluid appeared to be frozen like a glacier. In addition, she couldn't stop pouring at the right time since she was unable to perceive the movement in the cup when the fluid rose. In a room where more than 2 other people were walking, she felt very insecure and unwell and usually left the room immediately because people were suddenly here or there, but I have not seen them moving, she said. She could identify cars in the street without a problem, but of course she couldn't cross the street herself, since the car would seem far away one moment and then right next to her the next. In the same book, Oliver goes on to describe in detail the case of Virgil, a man whose thick cataracts had left him nearly blind since childhood. Not long before his wedding, Virgil underwent an operation to remove his cataracts when an ophthalmologist discovered that the original diagnosis he was given was incorrect. After 40 years of blindness, Virgil's first sightings were of his bride-to-be, and at first, the surgery seemed to be a resounding success. But in her journal entry the next day, Virgil's fiancée, Amy, began to write about the problems. Speaking to Dr. Sacks, Virgil admitted that those first moments of sight were incredibly confusing. He didn't know what he was seeing, and the light and motion and colors just seemed like a meaningless blur. What was hitting Virgil's retina was essentially the same as everyone else's. It was his upstream visual cortex that wasn't functioning as it should. And that's because we learn to see. Virgil was like an infant who can't make sense of the stimulation. And that's what the rest of our visual cortex is doing, taking the sparse information from our retinas and building it into a rich visual experience. It's not just about translation, as the myth suggests, but about recreation. When he met him, Virgil reminded Oliver of a previous patient, Dr. P, who had visual agnosia, an inability to recognize objects. Dr. P couldn't make sense of facial features. Instead of comparing the relative relationships between eyes, nose, and mouth, and seeing the face as a coherent object like the rest of us do, Dr. P would fixate on one feature at a time. Note that this is the most extreme version of prosopagnosia, milder versions of which are seen in people who can see that a face is a face, as opposed to a collection of independent parts, but can't attribute that face to a specific person. Returning to Virgil, he had trouble judging distance and jumped whenever a bird got too close, though, as his fiancée explains, the birds never got close enough to actually touch him. It's just that he had no scale for distances. He didn't know where one object ended and another began, and supermarket aisles were long jumbles of incomprehensible stimuli. He would get confused by his own shadow, illustrating just how much we take for granted the ability to adjust our object recognition with changes in lighting. Steps were torturous as he couldn't see in 3 dimensions. And ultimately, Virgil's story is a tragic one, as his health declined rapidly and he lost his sight completely, such that it was even worse than before the surgeries. But having become once again, and this time completely blind, Virgil eventually felt a sense of relief. Relief at being released from the incredibly difficult, if not impossible, job of learning to see in adulthood. Depth perception, object recognition, luminance, color constancy, all of these higher-order visual processes were unavailable to him. And so his case illustrates to us just how much our visual system changes the initial stimulation from the retina into a set of signals that are actually useful to us as we wander around the world. Photons of light are not sufficient. We need to fill in the gaps of our vision, group stimuli into objects, recognize them, figure out which ones are moving and where they are in space. We even have a blind spot in our retina where the nerve fibers exit the eye, where there are no photoreceptors. So we can't detect photons in that part of our visual field. Yet, we don't walk around with a black hole in our vision, even though the blind spot is not that far from the center of your field of view. You don't notice it because your brain is filling it in. In the same way that the visual cortex fills in information from our blind spot and allows us to perceive objects as constant despite their being occluded by other objects or illuminated with different lights or in motion, our other senses also take liberties with the raw input. In the case of hearing, for example, we can use the differences between what each ear hears as information relevant to where the sounds are coming from. And while we perceive boundaries between spoken words, this is an illusion, as an analysis of the waveform demonstrates. Just imagine what it's like to hear someone speak a foreign language. It's next to impossible to figure out which sounds belong to distinct words. And yet in our own native language, this process is effortless. Each of these processes, whether they're involved in hearing, seeing, or another sense, requires a different set of computations, often accomplished in disparate regions in the brain. The fact that vastly different parts of the brain process the nuts and bolts of different senses goes against our subjective experience of the world. It doesn't feel like my eyes are seeing one thing and my ears hearing another. The whole perceptual experience feels seamless. And even if I can isolate my hearing or my seeing by paying attention, each sense feels coherent within itself. I don't get the sense that my visual system is taking apart the world and then putting it back together for my sake. It just feels so seamless and effortless, which is amazing given how hard it's been to get a computer to come even close. And this paradox is what psychologists call the binding problem. How can a modular organization of the brain lead to a seamless, subjective experience of the world? To get a sense of how hard this problem is, think about an object, anything from a chair to a puppy to a skyscraper. You see the object as a constant. You effortlessly identify it, seeming to know intuitively where the object begins and ends, and even if part of it is occluded by another object, like a chair behind a table, or washed with a different light, like a skyscraper partly shadowed by another, or even a mess of puppies all playing together. How does our visual system know that the legs belong to the chair and not the table, especially if they're the same color and texture? How do we know that the two parts of the building are connected even though the light they emit is vastly different? How do we pull together all the different perceptions of the puppies as they move and change position? It's not just about memory either. When we encounter an unfamiliar and odd-shaped chair, we still don't mistake part of it for a table. So our visual system can't just be using templates. But we can learn about how the brain solves the binding problem, at least when it comes to vision, by studying what happens when it makes a mistake. In its simplest form, binding is the brain's way of combining two distinctive features, say color and shape, into one coherent percept, like a blue circle. But under some conditions, we can catch the brain making an error, what we call an illusory conjunction. Say, when it sees a blue circle embedded within green squares and interprets one of the objects as being a blue square. We see more of these illusory conjunctions when we're not paying attention to the object directly. So either we're distracted by something else, or it's in our peripheral field of view, or when a similar object is nearby. You've probably noticed this yourself if you've ever caught yourself, say, seeing a road sign and mistaking the words for something else. Let's say you see a crossing of Rose Court and Wood Street. Maybe you perceived it as Rose Street and Wood Court. And patients with damage to the left parietal lobe, a part of the brain that we call an association area, that seems to be involved in bringing information from different senses together, make more of these types of errors. For example, patients with a disorder called simultagnosia can't perceive more than one object at a time simultaneously. And then there's Anton Babinski syndrome, complete blindness, but with denial of illness. That is, a blind person who believes that she can see. Usually the syndrome happens as a result of a stroke, but it's very rare because two different brain regions have to be simultaneously affected, the visual cortex and the part of the brain that informs us that we can see. These patients walk around as though they can see, but they bump into objects and they often hurt themselves. And if asked what they can see, they confabulate, giving a detailed but completely made-up description, suggesting that some part of their upstream visual processing might still be intact, but it's not bound to the perception. We still don't know exactly how binding happens, but probably the best hypothesis is the idea that binding is an emergent property of the synchronization of many neurons firing. When the neurons begin to fire in synchrony with the same oscillations, the idea is that the perception of different features becomes bound into one object. Synchrony is attractive as a hypothesis because it can be both flexible, changing according to the conditions and a person's attention, and dynamic, quickly binding features together. It can also happen across long distances in the brain and can be modified with learning. So I hope you can now see the error of assuming that our senses represent the world exactly as it is. This can't possibly be true. We pick and choose only a small sliver of information to process, and then we take little bits of information, and with experience, our brain learns to fill in details, bind together different signals, and give us a perceptual experience of the world that we can actually use.